Okay, so I'll try to cover one topic, which is how we can expand the vocabulary in existing LLMs, right? So the idea here is the following: that suppose you have trained a language model and you have first kind of curated the data. So if you see the entire pipeline, the entire set of steps to train up LLM are the following: that you have curated the data. So maybe this is your curated data from different internet sources or from some books could be there, some online websites could be there, right? So all these are different sources of the data. News articles are there, so you have curated the data and this is your whole data. So maybe this could be in GBs or in TBs, right? Then you this is your data, right? And then maybe you have done some sort of pre-processing, you have deduplicated the data and you have done some sort of pre-processing on this data. So this data suppose has got pre-processed, right? Then you have this new version of the data is smaller than the earlier one. So suppose this was 100 GB, so this probably becomes somewhat around maybe 80 GB. Okay, then what you do is maybe you can pick 2% of this 2% of this data or 3% of this data, some random document, 2% of the random document, 3% of the random documents, right? You create a small random subset, right? And then once you have created that random subset of that data, you train your tokenizer on this small subset. Right. So this is, and we have seen how what are the different types of tokenizers and how to train them, what is the vocabulary that we have to fix in the beginning, right? So this trained tokenizer is kind of the backbone of the entire LLM. Right. So then once you start training your actual large language model, you are going to take, so whenever you have a stream of characters, you will pass it through your tokenizer, which is the trained one, right? So this is your tokenizer. So you have a stream of tokens coming into it, a stream of characters. You pass it through your trained tokenizer, right? Trained tokenizer will break it into tokens, right? And then you pass those tokens to the language model. So this is how the training happens, right? And then you're based on the use case, the way your architecture of the LLM is, it is going to generate tokens and train itself. Okay, now one thing which has kind of over the time we have seen is the following: that most of these language models are trained on the text which is English, very English heavy, right? So maybe almost 99% or even sometimes even just this entire data on which the LLM is going to be trained or these tokenizers are trained, that is English. Okay, so if your tokenizer's vocabulary contains all English characters, right, or all English words, then you cannot kind of create or train a mod LLM on for other languages. Right. So that means most of the times when you see, or most of the language models which you see these days, the popular ones, the big ones, they are heavily trained on English. So that's why their performance is not very good on other languages. Okay. Because they are kind of primarily trained on English or primarily trained on English and they're for English. Okay. So that's why they don't do well on other languages. Okay. So one thing which has been shown is that this tokenizer that you have trained is some sort of tied to this LLM. Right. And if you want to, this is how the training of LLM happens, right? So this tokenizer is somewhat tied to the LLM. And if somehow you want to change the tokenizer because you want to, maybe you want to expand your language span, maybe from English, you also want to expand your languages to Hindi or Gujarati, Malayalam. These are Indian ones. Spanish, French. So then what you have to do is, it is not just the tokenizer that has to be changed, it is the LLM that also has to be trained from beginning. Okay, so this actually process, or this type of phenomena is called where a tokenizer is being tied with the LLM, right? And if you have to change one, this entire the other thing has to also be changed, or it has to be trained again. Okay, and that is a big problem, right? So, and in order to kind of address this issue, a set of papers have been proposed where the idea is the following, that you don't have to pre-train this language model from the beginning or from the scratch. What you have to do is you have to make some changes in the tokenizer so that the tokenizer itself is adopted for more languages. Right. So when I say more language, it is not just for more language, it could be for other domain also, right? Maybe your LLM has been trained for a very specific domain. You want to expand it for other domains. Okay, in that case, maybe the tokenizer has to be changed. So, right. So this is where the set of models, the set of kind of methods have been proposed, and we are going to see those. Okay. So this is a kind of a very generic pipeline in which kind of uses this vocabulary expansion techniques to expand LLMs, to expand language models to other non-English languages, right? So what you do is the following. Suppose you have an English LLM. You have a trained very good English LLM. Maybe you can talk about that, maybe Llama, right? It's very kind of a very good quality language model trained in English, right? Now you have some vocabulary expansion technique. Some technique, we'll see what technique I'm talking about, and you have expanded the vocabulary, right? Once you have expanded the vocabulary, you ideally have to do some sort of continued pre-training on somewhat new data, right? So suppose your model was trained on English, maybe once you have expanded your vocabulary, you have to continue training or continue pre-training of this English LLM on some Hindi data. Suppose you have expanded your vocabulary to some Hindi tokens, right? A Hindi or mix of English Hindi, that is also possible. Okay, so some continued pre-training. Then you have to do some human preference alignment. We have seen this kind of the this particular pipeline where we do first instruction fine tuning, and then we also do some sort of human preference alignment. Okay, and finally, whatever you get is the multilingual LLM. Okay, so if you see here again, from one language to more languages, right? So it is not just you have to change the vocabulary, you have to do some sort of pre-training also, you might have to do some sort of instruction fine-tuning also, you might have to do some human preference alignment also specific to different languages for which you want to expand it to, right? This pipeline in general holds true, right? Different methods for vocabulary expansion might not require all these different steps to create this final multilingual LLM from a monolingual LLM. I hope you are clear what is the difference between monolingual and a multilingual LLM, right? So, and again, this depends on this vocabulary expansion techniques. We'll see 2-3 different techniques today. Fine. Any questions till now?
Sir, I was just wondering, let's say, this English LLMs are like very good at doing the English task, right? And let's say we have, so let's say we have an English LLM, and then to get a multilingual LLM, we just like have, let's say we query in English, and all the input and output is in English. But let's say after this LLM, so whenever we generate whenever we generate, let's say some output, so we have a translation done which just like translates. So like it's a very good translation, like ideal one, like how we want it. And whatever it will take the input like English as the by default language, and then it will generate to XYZ languages. So that could be, let's say,
That is possible, but over the time, there are some papers which show that this approach doesn't work very well, uh, while we want to transfer languages. Okay, mostly because so again, there are some other issues also. One of the issue is that maybe much of the information for which suppose we want to train our model in Hindi, right? But no Hindi model is available, we have only English models available. So most of the times when this English model was available, it is trained on, but it might not even have that knowledge itself. Fine. So
Yes, sir.
like if the knowledge is present in English, then probably this translation will work. But if suppose the knowledge itself is not present, then how are you going to answer that?
Yes, yes.
Right. So that is one such reason to kind of train language models for different languages.
Yes, sir.
Okay. Yeah. So this is one. Now, now the thing is that why? So suppose we do something, right? And then what is the actual problem here? So suppose maybe we can. So what is the problem with the current model, right? So suppose we have picked llama, right? Now we want to do one thing that it works very well for English. Now we want to just don't do anything. We just pass some Hindi data, right? So anyway, the way these model tokenizers are created, or whatever string you will pass, they are going to be created. It will kind of split it into subtokens or subwords. Okay. So the problem there is for non-English data, the number of subwords are going to be much larger or much bigger than what you will find in case of English. Okay. So in that case, the inference speed is also going to be impacted, or the amount of time to answer a given query, even though model knows how to answer it, right? It is going to be larger, right? Not just time which it takes to answer, for which the time difference between an answer in English answer and a Hindi answer, it is also the cost, right? Most of these language models, the pay model is the following, that it is going to be based on the number of tokens the model has outputted, right? For the same answer, you have to pay more for a non-English language answer than for an English answer. Okay, so these are some difficulties. These are some of the problems that still all these monolingual language models face when we try to transfer them directly from English to non-English languages. Okay, so again, so now this is we are going to see this, how we are going to expand the vocabulary, right? Again, this is a very generic pipeline. So suppose you have a monolingual data, right? We already had a monolingual data. We trained a tokenizer on this. Okay. Now you train the tokenizer. This is your new vocabulary, right? This is your existing vocabulary. So maybe this existing vocabulary is for English. This monolingual data is from Hindi, right? You have trained your tokenizer. So whatever tokenizer you have trained, right? And you got a new vocabulary, right? So earlier, maybe in case of llama, suppose you have 30K vocab size, maybe you find out that maybe 8K tokens are sufficient. So the new vocab is going to be 30 plus 8 K number of tokens. Okay, this is your extended vocabulary, right? So what is the challenge here? This is just the vocabulary that you have created, right? Combining the English one and the Hindi one. What is the bigger challenge here? The bigger challenge is the embeddings, right? So in the language model, in all these LLMs, you have two embeddings. One is at the bottom and one is at the top, right? This is the input embedding, and this is the output embedding, right? What does this input embedding does? Given a token, it generates a vector corresponding to that token, right? And what does this output embedding does? Given a vector, it generates a probability distribution over the words in the vocabulary, right? So we have to also change this input embedding, because this input embedding, earlier, what was its size? Its size was whatever is the dimension, the vector dimension, right? And it also depends on the actual vocabulary length, right? So if earlier it was 30K, so it is going to be 30K into maybe if it is D model, so I can say it's D model, right? Now the new vocab input embedding size ideally should be this much, 38K into D model, right? Both input embeddings and output embeddings are same, just a copy of each other. So similar things are going to happen at the output side. All right. So that means, yeah.
Do we have to retrain the embedding?
We have to do that, yes.
So why is that? So we need to retain the embedding. Say for English, so for Hindi, okay, it's I got it. We have to retain, but say our model is trained on a English data set, which is a 30K. We can just append the Hindi vocab and just only retain the Hindi vocab.
There are different methods. I'll talk about that. I'm not saying that you have to retrain these input and output embeddings like from scratch to make the things fast. We will talk about that.
Okay.
Okay,
And
but the idea is that these input and output embeddings are going to change. Okay, and for that some training is going to happen. Yes,
okay,
go
and
ahead.
there can be duplicacy.
Yes, it can be there. Duplicacy in terms of what?
Tokens. So in Hindi data say Hindi vocabulary, I can have English tokens like
It is possible.
numbers.
Yes, people have not talked about that, but it is possible. Yes.
Okay.
Yes. So ideally, when you are going to append the two different vocabularies, it is like you have to first check it whether there should not be any duplication. Because if something is already there, you don't need to create a token for that.
Okay.
Right. So papers don't talk about it, but yes, paper, I think they do it. They kind of check before they append the two vocabs together.
Okay. Then how they decide which tokens to keep and which tokens to remove? Like English to remove or Hindi to remove if
No,
they are
see, at the end, the vocab that you get is going to be a unique set of tokens.
okay.
Right. Now,
Yes.
that token, whether that appears in the English text or it appears in the Hindi text, doesn't matter. It is going to
Okay.
represent both.
Okay. Got it.
Right. Fine. So this is how things are. This is how things are done. Okay. So once you have expanded your vocab, you are going to retrain your embeddings. I'm not saying a complete retraining. We'll talk about that. But embedding these matrices, this embedding, input embedding and output embedding matrices are going to be changed. Okay. And so this is your base LLM. This is your base LLM. And you are going to initialize these new embeddings. You are going to train them. And finally, whatever you will get, a new LLM with extended vocabulary. Okay. We will see how to initialize these embeddings, right? There are different methods and we are going to talk about that. But this is a general kind of a general pipeline to expand the tokenizers vocabulary for different languages. Okay, so the three very popular methods to initialize the new embeddings, right? So the idea is that suppose you have decided that, see, this is my vocabulary going to be, the new vocabulary is going to be, right? You have to change those input embeddings and output embeddings, right? So one possibility is that you just initialize it. You are anyway going to do some sort of pre-training and fine-tuning of this new language model. Okay, but an initialization of new embeddings is required. So one possibility is that you initialize it using a normal distribution. Okay, why this is popular? It is a very simple technique, right? Whatever new embeddings you have kind of created now, you just have to initialize all the cells using using a normal distribution. So, but it is a simple one, but it takes large amount of time in final convergence. That means you have to retrain or further continue training your LLM for a longer period of time. Okay. Another possibility is the following. Why not I take the average of existing embeddings? Right. So we already had some embedding matrices, input embedding matrices. Now I take the average of the subwords, right? So for example, the idea is the following, that maybe this was my embedding matrix. So I have maybe words W1 till WN, and corresponding to that, the vectors are there in my input embedding. Let us just talk about input embedding. Right. When you added some more words from Hindi, suppose your input embedding is like this. Right. Till here, you have words from English and their corresponding weights, right? And from Wn plus 1 till Wm, n plus m, I should say, because you have added m English words, right? Hindi words. So these needs to be initialized. Okay. So one possibility is I just initialize these weights using simple random distribution or a normal distribution. Another possibility is that I initialize these weights from these vectors corresponding to the new tokens that have come from another language, from wn+1 to wn+m, by using the existing embeddings, right? So what we have to do is we have to pick this particular word. You have to just split it into tokens. And which tokenizer we are going to use? The older tokenizer. So you have some word here, some Hindi token here. You split it using the older token. You will get subwords. You pick the embeddings for those corresponding subwords. You take an average and just keep that particular averaged vector here. Right. Similarly, you pick another word, the next Hindi token. You again use the previous tokenizer, break it into subwords, pick those particular subwords from this matrix, their corresponding vectors, average them, and put back into them here. Okay, so this is again another technique which people have proposed, right? So again, limited change in the existing vocabulary distribution, because all the previous weights are going to be exactly the same. We are not changing it, right? Only the new weights we are changing. The new vectors corresponding to the new tokens from the new language which you want to add. Okay, so once this is done, this is the initialization. This is how you are initializing input embedding, right? Further, you just pre-train it on some number of epochs, maybe for some iterations, and it will kind of get trained. It will get converged. Is going to converge, right? But what it says is the following: even though this technique looks simple, and it is going to require very limited change in the existing vocabulary distribution, but it will still have a larger convergence time. This is what has been shown using different experiments. Finally, third technique which has been proposed is called weighted average. So this was just simple average. This is the weighted average of existing embeddings, right? So again, we are going to do the embeddings, do the average of the existing embeddings for the new tokens, but this is going to be the weighted average, right? Now it has been shown that again this is going to perform limited change in the existing vocab distribution, but the best part is that the convergence time is kind of very low in comparison to the other two techniques. Okay, we will talk about these two techniques now. Okay, so first technique is something that I already told you, this average initialization. Okay, initialize new tokens to the average of the embeddings of the existing tokens. Fine. And it has been shown that the KL divergence between the pre and post expansion of LMs for the existing vocabulary, that is very less. There is very less. So over the time, when you have kind of expanded your language model with more vocabulary, right? The previous tokens which were there for English and the new, because you are anyway continued training your LM, right? So the new input embeddings for English, the KL divergence is very small. So that means there is not major change in the English embeddings before and after you have expanded it. You have expanded your vocabulary. Okay, and then
Sir,
again, this is
can you tell the point number 1 again, the new token, and I didn't
so
got that point.
no. So the idea here is that suppose you have this vocab, right? So you have this vocab W1 till WN. This is for English, right? And then what you have done is you have added M number of words. And these new tokens have come from Hindi. This is the English one, which the model is already trained on. Okay, you have the trained input embeddings. Okay, now what you'll do is, so for W1, you have a vector, the input embedding vector. For W2, you have the input embedding vector. For W3, you already have a trained input embedding vector. Same is for WN. But we do not have a trained input embedding vector for WN+1 till WN+M. Okay, because these are the new tokens that have just entered your vocabulary. So what you're going to do is, you are going to break this particular, or you're going to split this particular token in terms of the existing tokens. Right, so what you're going to do, you just pick the older tokenizer, you pass WN+1 to it, will break it into subwords.
But for the Devanagari script, the older tokenizer won't be able to handle it, right?
So if it is suppose byte pair based tokenizer, it will be able to do it.
Okay.
Right. So if it will be able to do it. Right. Otherwise, it always has this option of not out of vocabulary thing.
So then it will be generating unknown for all the tokens, for
Yes,
all the
yes,
dynamic
yes. It
scripts.
is possible. Yeah. So it is always possible that all the words are out of vocabulary was, and that is what it also says. What if all
Okay.
new embeddings have been initialized to the same value, and that would be out of vocabulary.
Okay.
Right. So that is possible, right? But idea is that you just split the new vocab in terms of the older vocabs, in terms of the older tokens. Okay. And then you just average over the embeddings of the
I
existing
think,
tokens.
yes, this can be happen with French and English or Spanish, like
Yes,
those
yes,
language.
yes, yes. So
Great.
if the scripts are very similar, then possibility is that like you will get a very reasonable average embedding. Right. But scripts are different, and it is highly likely that you might find most of the new tokens to be out of the vocabulary. Okay, fine. So this is how this simple technique works. But again, the problem here is that the convergence is going to be very large. It will take a lot of pre-training steps to further tune these new embedding bits. Okay, fine. Again, this is not very important. Maybe I'll just talk about this later when I'll be talking about one method. Okay, the one of the potential issue is what if all the new embeddings have been initialized to the same value, which is possible that maybe all of them are just OV. Okay, in that case, you can add a small random noise to the average embeddings. Okay, so in that case, maybe all the embeddings are slightly different from each other, not exactly the same. Okay, now this method, the third method was this, that the second was average of existing embeddings, the third was weighted average of existing embeddings, right? So I'm going to talk about one specific method. This is called WECHSEL. It is a type of a method where you are going to take a weighted average of the existing embedding to create embeddings, input embeddings for the newer tokens. Okay, so this method looks like this. Okay, I'll give you some definitions. Again, in this presentation, I'll be only talking about models, or I'll be only talking about methods, not the results. Okay, so results and what experimental settings, you can go and see the paper. But whatever has been proposed, I'll just explain what they have done. Okay, so here, suppose you have a source model, right? Maybe the source model was in English, right? So in the source model, you have three things. In the source model, you have non-embedding weights. What are the non-embedding weights? Anyone, any idea? Suppose we are talking about llama, right? So what will be the non-embedding weights?
All other parameters like attention and feed forward network parameters.
Yes, so everything which is not embedding, right? So embedding you have at the bottom and the top, that's all, right? In between, all the weights that you have, those are all non-embedding weights. So attention weights and the feed forward weights. Okay, and then so these are the non-embedding weights in English model. Then you have the embedding weights. We are calling them as ES. Okay, whether this is input or the output, let us just, both are again most of the times the copy of each other, so let us just call them as ES, right? And then you have the tokenizer. Okay, so TS is the original tokenizer for English text. Fine. Now what we are going to do is this tokenizer TS, and this is a tokenizer for the source language, and similarly this is my target model. I want to update my vocabulary, and my target model will be this. Okay, it is also going to have non-embedding weights, it is also going to have embedding weights, and it is going to have a new tokenizer TT, right? So TS is this tokenizer, the source one. TT is the new tokenizer where we are going to append more words, more tokens from maybe Hindi, right? So Hindi, maybe let me just call that this target model is a Hindi model, Hindi plus English. Okay. So that for TS, my vocab was US, right? So my vocab was US. So maybe in case of llama, this could be 30K tokens that are part of US, right? And for TT, the new one, which we are going to, the new tokenizer is going to have UT, right? The new vocabulary. And maybe this is going to have, say, 30 plus 8K tokens. Fine, it is going to have more tokens. Fine. So what are you going to do? What are you going to do is the following, that for both source, okay, one more thing. So when you are going to train this model, this target model, because this English model is already trained, right? So you are going to simply copy all the non-embedding weights directly to the non-embedding weights of this target model. What is going to be changed here is these embeddings. This is what this model proposed, right? You don't have to play anything around these non-embedding weights. What you simply have to do is you have to simply change this older embedding to the new embedding. This new embedding is the average, weighted average of the existing ones, right? How will you define the weight? That is all this paper is about. Okay, so what they have said is the following. Suppose for this particular source language and for this target language, independently, what I do is I will create two embeddings, WS and WT, right? So they are independent of this language model which you have done, which you have created, right? So this is what this matrix is, what these embeddings WS and WT are. So they correspond to maybe all words. Suppose WS I'm talking about. So this embedding is for all words in English, right? Plus n-gram subwords in English. Right, so WS is a embedding for all words in English, right? Plus some popular n-grams in English. N-gram subwords, I should say. Okay, so and WT is again all words in, maybe you can say Hindi, and plus n-grams in Hindi, something like that you can say. Fine. Okay, now what is this aligned says? So what this says is the following, that we have this matrix, we have this WS. So what is this? WS is a matrix. The number of rows are going to be the all words in English plus n-gram subwords in English. And maybe you have a vector corresponding to each of the token, each of this word and n-gram subword. That is my WS. Similarly, you have WT. The only thing which is common between WS and WT is we have kind of alignment between these two matrices, WS and WT. What it says is, maybe if suppose you have a word mango in English and you have a word in Hindi, right? So this mapping is present, that this particular embedding is aligned to this particular embedding, or this particular token in WS is aligned to this particular word in WT. Okay, so this alignment is there. The way, this is how they are trained, right? So the way they are trained in maybe n-dimensional space is the following, that two words which corresponds to same symbol. When I say symbol, so or mango is one symbol, right? So if whether it is represented in English or whether it is represented in Hindi in an n-dimensional space, both of these vectors will be very near to each other. Okay, this is what aligned word embedding represents. Okay, and these are static representations. So you just pick one language, you just pick another language, you train a model. So there are nice models which can be trained to align embeddings from different languages. So those are very popular models, right? But whatever they are going to create, finally these WS and WT, these are static models, static embeddings. Fine. So these embeddings are already present. You don't have to do anything. For source as well as for the target separately, they are aligned also. Fine.
Sir, what about
yes.
the subwords, n-grams in these matrices? Are those also aligned?
Yes, they are also aligned.
I mean, how? I mean, what is the relation between the n-grams? I mean, there could be some n-grams which won't mean anything, right? So.
I completely agree. So I think the way they have trained these embeddings is the following: that they have picked some popular n-grams. Okay, not all possible n-grams. And sometimes they don't mean also. That is also fine. Yeah, that is possible. Right, but this is more on the based on the frequency.
And I missed it. Like, what was used for aligning these embeddings? These.
So I have not talked about specific methods, right? So I think they mentioned some specific method which was used for creating these aligned embeddings. Okay, but there is existing literature. So the novelty of this paper is not on this alignment. What they said is we use a pre-existing method to create aligned embeddings for the source language and for the target language.
Okay.
Okay. So once, yes.
So one needs to get the vocabulary again for this embeddings to get these embeddings, right?
Yes. So this is not restricted like the way we restrict vocabulary size in tokenizers.
No, the thing is we already had a vocabulary for our English model.
Right.
Now I agree that we create a vocabulary for our Hindi model, but for English model which was already present, we again have to create the vocabulary. Its vocabulary. Then it will be a very tedious work, right?
No. So see, the idea here is that we don't have to do it. These embeddings are already present for different languages.
Okay, they are available.
They are available. Yes.
Okay.
So these aligned embeddings are static embeddings. You don't have to train a language model, right? So this is a entirely different idea to how to create this aligned word embeddings, right? And these are very language specific. They are already present. Okay. You just have to download them and you can use them readily.
Okay.
It is a different question whether one is better than the other approach. That's a different thing, but they are available. Okay. Now, once you have these embeddings, what you do is for each subword that you have in TS, right? You can use, so for each subword that you have here in US, right? So each subword that you have in US, you can find out its specific embedding from here. Right. Same thing you can do from UT also. So all the subwords which are part of UT, you can find out their subword embeddings from here. Right. And once you get that subword embedding, what you have to do is the following. So finally, what you have is for all the subword tokens, for all the tokens that were in the tokenizer TS, right, which were created by the tokenizer TS, you have their corresponding embeddings. You are calling them as maybe they're coming from this WS, right? And similarly, all the tokens that will be generated from TT, there for each token, you have embeddings that are coming from WT. Okay. Now, one thing which is clear is that whatever these embeddings are going to be, they are aligned with each other. Okay. So what we'll do is I will pick one token from here, right? And I will find out its similarity with all the tokens in TT. How I'm going to do that? I'll use this metric. Simple cosine similarity. Right. So I'll pick one token from here based on this embedding that is already present. Right. I will find out the cosine similarity with all the possible tokens in the vocabulary T. Okay. So this is what this is saying, right? And so if suppose this has maybe 30K tokens and this has 8K tokens, so we are going to perform this many number of cosine similarity computations. Okay, so where each word has some similarity with the other word. With this zero, that is a different thing. Okay, now what you are going to do is, finally, what we have to do is the following. So each word, or you can say the other way around, each word here has some similarity with each of the word in this particular vocab. Right. Now what I'm doing is I'll fix my K. Maybe K is suppose 10. Okay, so K 10 means that for each token that is there in the target language, I am going to find out top 10 tokens in my source language based on the similarity, right? And what I'm going to do is I will create the embedding for that particular token using this formula. What does this say? So you pick K top tokens in S, right? We are going to take their vectors or their embeddings, and we are going to use this particular weight before we sum and take an average. What is this value? This is just an exponent of this similarity, right? So the weights, the way we are going to perform this weighted average is we find out what set of tokens are similar for a given Hindi token. I'll pick the top 10, right? Now I'll pick the embeddings of these top 10 vectors, and I'm going to take an average of that, right? How are we going to take a weighted average? I'll use this similarity values for this corresponding pair, right? I'll just take a exponent of that. The T is some this is called a temperature, so they just call this a temperature. In experiment they kept it as 0.1. Okay, but this is how they kind of created these weights, the weighted average initialization. And they have shown that if you perform the weighted initialization, you require very less amount of data for the target language to further train this model. Okay, so earlier they showed that maybe it was kind of taking somehow 30 billion tokens, right? But right now it can just take 0.1 billion tokens, and it will give you similar kind of a performance. Okay, so this model has been very popular over the time. This is called WECHSEL. Okay. Another model which has been proposed is this. This is called zero-shot tokenizer transfer, right? Here, the idea is that the new model will see very less number of, almost zero number of tokens from the target language to train these embeddings. Okay, the idea here is the following. I'll just showcase the idea, like what exactly is going to happen. So what happens is the following, that they are going to use a hyper network. Okay, so the model is this. Let me just introduce the model, right? So the model is, this language model is this, right? It has input embedding and it has a output embedding. Initial input embedding was this. These were my initial embeddings, right? This E5B is the final embeddings after vocabulary expansion. Okay, so how do we get from E5A to E5B? By using a hyper network. That is what we want. You expanded your vocabulary, you want, then you have to train your embeddings, you have to initialize it, you have to further train it, right? So how are you going to train it? And you are going to use a hyper network to create these embeddings, right? So if you see this, this is the new tokenizer VBTB. So earlier it was VATA. Now you have the new tokenizer VBTB, right? So you pass these tokens to this hyper network, it will generate the embeddings for the new tokens, and you can use those new tokens embeddings like to embed and to kind of concatenate to sum it with the positional embeddings, pass it to the LM, and do the rest of the things. Okay, the idea here is the following. So this is the loss, right? This is the loss of LM, loss of this language model. It is the cross entropy loss, and it is dependent on three things. One is the tokenizer, the loss that will happen because of the tokenizer. This is What are these? Phi A,
Embedding
Phi
of
A
the
and Phi
older.
B, the embedding parameters, right? And these are the non-embedding parameters. Right. So this is the loss that you minimize whenever you create a language model. What we want to do is we want to train our hyper network such that we have to minimize this loss. So our embedding weights, non-embedding weights are going to be as it is. Fine. Our tokenizer will change from TA to TB. And what is this phi A? So phi A are the weights, embedding weights, right? Now these embedding weights are going to come from where? These embedding weights are going to come from the hyper network. So this is the hyper network. You are passing the new vocab and the tokenizer, it will generate the new weights, the new embedding weights, right? So now this is my new loss function. Okay, and we have to train the hyper network so that you have to minimize this particular loss. Okay, so we don't make, remember one thing, we don't make any change in the non-embedding parameters of this language model. We just train this particular hyper network. Fine. So how do we do that? How does the hyper network looks like? So suppose, yes. So suppose this is your tokenizer, the new tokenizer TB, right? And some text is given to this particular tokenizer and your vocabulary has also been extended. Okay. So suppose this is your new tokenizer TB and this is the vocabulary. The new vocabulary. Okay. What you're going to do is, this is your hyper network. Fine. Now what you're going to do is the following, that you are going to break, or you are again going to split the new vocabulary in terms of the older words, older tokens, based on this VA, right? You are going to tokenize VB based on VA, right? So this is one possibility, that underscore the is now simply will be written as underscore the, because the was present before also, right? The new word is could be flower beds, underscore flower beds, right? So here you are breaking it into, splitting it into flower, bed, and S. Okay. Among A and Monk. Okay. So the idea is that in the hyper network, you are going to split the words into individual tokens, individual older tokens, right? And you are going to pick the embeddings, the input embeddings or the word embeddings from the older embeddings, right? So if you see this, this is the older E phi A for the underscore the, right? This is E phi A underscore flower, and so and so. Fine. And then what you're going to do is you are going to pass this
Hello.
entire embedding to a HLM, right? HLM is again another language model. Just 1 second, Ankit. So you just pass these embeddings, you compose these embeddings, you pass it to the new language model LM, and you actually have to train this particular language model. So what this language model is going to give you, an embedding for an embedding for flower beds, an embedding for among, an embedding for all the words that are there in your new vocabulary. Yes, Ankit.
So the vocabulary, the second vocabulary will be dismantled in the merging of first original vocabulary, right?
The second vocabulary, the new one or the old one?
This VB, the new one.
The new one, yes, yes.
Why we are doing some? I mean, we have already created a vocabulary, right?
Mm-hmm.
So
No, we have just
we
created
want
the
the rules of original vocabulary to be
yes,
implemented on the new vocabulary.
yes, yes. So we don't want to completely forget what model has trained using the original vocabulary, right? So this is the first step which you have to kind of train this language model, this particular hyper network in this case, that you break or you split the new tokens into, in terms of older tokens, you pick the older embeddings, right? And then you pass that composed embedding into this language model, which is again a transformer model only, right? And the output of this transformer model will be the new embeddings. which can be used later.
But again, this will be only working for the scripts which have same basis like English or any other Latin
I
script.
agree. Yes, it is true. Yes, it is. Yes, right. In other case, so see so when you have created your older ones, you might have taken care of the situation. What if some word has come and I have to embed it maybe using OOV? Okay, so there must be some tokens that will take care of that.
Okay, sir.
Right. So yeah, that is how it is.
We could just map some of the Devanagari with the some of the subwords from English.
Yes. So we can do all this, but this is how it has been proposed. Right? Again, there will be a lot of corner cases that are going to happen. Right. Okay, so this was another technique. So this is called zero-shot tokenization transfer, because you actually don't do any sort of updates on this LM. Right, you keep it as it is. It is the hyper network which is getting trained. Fine, so you don't do any sort of training at the LM side. That's why people call it as a zero-shot tokenization transfer. Okay, this
How
was
the
another. Yeah, yes.
hyper network is getting trained?
Yeah, the only hyper network is getting trained based on the loss which is calculated using this LM.
Okay, so we are getting the loss from the logics, right? Or
Yes, we are getting the loss from the logics.
okay, got it.
Okay, so when we are back propagating, we are not changing any of the weights here. We are actually changing the weights of this hyper network.
Okay.
Right. So in future, whenever we want to whenever we want to embed a word, we actually have to pass that word to the hyper network. It will generate the corresponding embedding, and then you use that embedding in the language model when the model is trained.
Okay, and in calculating the loss, the tokenizer won't be there, right?
No, it is not going to be there. Yes.
Okay.
Yeah.
Got it.
Yeah. Okay. Fine. And so this is the last technique. And again, this is not a technique. This is like the steps they have followed. So again, why I'm covering this paper? Not very popular paper, and again, not very popular paper, not published in any of the venue. But interestingly, they have shown different steps to how to kind of pick one sort of embedding or one sort of weights to train. Right. So what they have done is, again, this is a simple idea that you have some input embeddings, right? You have the LM and you have some embeddings before and after, right? And you have expanded your vocabulary. You have to re-update or re-change or kind of retrain your this input and output embeddings. So what you have to do is, in the preliminary stage, the first stage, you are going to tokenize, you are going to train your tokenizer, and then you are going to kind of initialize these embeddings. That is what we did, right? So your earlier, suppose your embedding was like this, maybe you have added some more weights here corresponding to the new tokens that have been added. Fine. One simple idea that they have used in this paper is simple average kind of expansion, right? The way we have done it, the idea number 2, that you pick one word from here, find out the subwords that creates this particular word, average their vectors to create this particular vector. Okay, again, this is simple initialization of this input embedding. Now what they have done is, they have now trained end-to-end this model, right, in different steps. So in the first step, they are only training new input embeddings. This is pre-training I'm talking about. So they are going to pre-train this model, continual pre-training of this model, but they are only going to update the weights of the new input embeddings. Only these weights are going to be changed in the beginning. Next time, and not even these weights, even though these are exactly same, right? In the next stage, they are only going to update the weights for these embeddings, the new output embeddings. So these are the input embeddings, output embeddings. These are the new ones. These are the older output embeddings, right? These are the older output and input embeddings. These are the newer input embeddings, right? Third stage, they are going to update both new input and new output embeddings. So both of these will be changed or will be updated in the third case, right? In the stage number 4, we are going to update all output embedding. So this entire output embedding matrix is going to be updated. In the 5th stage, we will update new output and all output embedding. So only this much, and this entire thing has to be updated. In the stage number 6, we will update end-to-end all the layers of this transformer model LM. And in the final stage, we are only going to train this internal layers of this language model, right? And they have shown that this works very well. They have done experiments on the Korean data set, right? And they have shown that it works actually very well for the Korean data set, for the Korean language model that they have trained on. Okay, so I'll just end here. I have another presentation at 4. Okay, I will cover this. This is again a very interesting slide that I have added here. I will present this slide maybe sometime on Monday, the first presentation. Maybe I can just present this slide, and then the speaker can start from here. Okay, so that's all from my side. Let me know if you have any questions. Maybe one quick question I can take.
Their sorting order, the order of their stages.
Yes,
They have given all the output embedding, but why not input embedding then?
that is what they have done. So they might have done some experiments. The explanations are not there in the paper.
Okay.
So this is the best kind of the sorted order of the different stages that they have proposed. Again, there is not explanation why this is the best.
Okay, got it.
Okay, but if they have done it for Korean, it might not be true for other languages. That is also true.
Okay.
Yeah. Okay, great. So I'll just leave, and but I'll talk about this last slide again. There's a very interesting slide in the next meeting. Okay. Thank you very much.